I'm not all that happy with the way I developed this part of the topic here. So I'm going to kind of recommend that people do watch the brief summary. Okay, so I'll say it kind of quickly, but we have the expression y equals f of x naught plus f prime of x naught times x minus x naught. We understand that f prime of x naught is the slope of the tangent line, and x minus x naught is the run from the point of tangency to the point where we have, well, to the point where corresponding to coordinate x. The run, therefore, from x naught to x is just x minus x naught. And f prime of x naught is the slope of the tangent line. So the rise of the tangent line divided by the run has to equal the slope. And it follows immediately then that the rise equals the slope multiplied by the run. So the rise is what? It's y minus the value here, which is f of x naught, okay, from here. And that's equal to slope times run, which is then f prime of x naught times x minus x naught. So this thing represents the rise of the graph predicted by along the tangent line from the point of tangency out to the point that's characterized by coordinate x. And we can also say, okay, rise over run is slope, so y equals f of x naught plus f prime of x naught times x minus x naught, original y value plus the rise. We actually started with a numerical example where we had a slope of 2/5 and a 0.23, and we saw that, okay, the run from this point to the point xy, where we're not sure what y is, but let's assume we know x, is going to be x minus 2. Because if we're at x here and we're at 2 here, then the run is x minus 2. So we go from here to here. So the rise, which is y minus 3, obviously, because if the y coordinate here is y, and this coordinate is 3, the rise is y minus 3. That's got to equal the slope times the run. And the slope times the run is just slope, which is 2/5, multiplied by the run, which is x minus 2. Okay? So, a lot of ways to write this. The slope is rise over run, so 2/5 is y minus 3 over x minus 2. Follows that y minus 3 is 2/5 of x minus 2. Y is 3 plus 2/5 of x minus 2. And this is also in the form of this, where the 3 is your known quantity, which we called y naught up here. So this is y equals y naught plus slope, which is 2/5, multiplied by the run, x minus 2. Just an instance of this. Okay, over here, then, we focus on the rise, okay, the change in the y value. Change in the y value is what? It's equal to slope times run, it's equal to slope times run, which is slope times delta x, and delta x is just x minus x naught, so it's slope times x minus x naught. And that, of course, is equal to f prime of x naught times x minus x naught, because the slope is f prime of x naught. And then we're just saying that the value of y predicted here is the initial value, y naught, okay, plus our delta y. So y equals y naught plus delta y, that's obvious. Okay, here's y naught, here's delta y, here's our new value of y along the tangent line. Delta y, again, being slope times run, is slope times delta x, is slope times x minus x naught, is f prime of x naught times x minus x naught, because the slope is the derivative evaluated at x naught. Okay, so that's what this picture is telling us, and I've commented you really need to be able to draw these pictures, understand, explain the things that are related by the picture. Now we come down here and we look at what happens if we have an actual function whose point of tangency is here. When I drew it, I didn't draw it real well. The point of tangency looks like it ought to be here, but let's pretend it's here. You still get the idea that this function is curving up and away from the tangent line. So the tangent line follows the function pretty closely, but then it starts diverging more and more. And it's this divergence between the tangent line and the function that we want to think about. There's a discrepancy between what the tangent line would predict and what the function actually does. Okay? Now, let me just look at the diagram for a minute, and then we'll talk about that. First place, we've got the y naught equals f of x naught, which is pretty much what we had here. The x naught, the x, the triangle, and the delta y. Now, for the delta y, I did fill in f prime of x naught times delta x, which is slope times run. And I wrote that out a little more, in a little more detail, as slope f prime of x naught times x minus x naught, which is what the run is. Okay, so this part of the picture, the white part of the picture, just mimics what we have up here. But now we also have our value that we get for coordinate x. We have our value of the actual f of x function up here. Okay, so we project up to the function and we get a value here. We call that y equals f of x. And now our y that's predicted by the tangent, I don't just call it y now, I call it y sub tan, the y prediction of the tangent. I could use y PRED for prediction. Okay, other things I could use. And we see that the change in the function from x naught to x as predicted by the tangent line is just this, which is, of course, the difference between here and here. Whereas the change that actually occurs for the function is this. In other words, the difference between this value y naught equals f of x naught, and y equals f of x. Okay, now both functions start. The tangent line starts at the point x naught, y naught, and the function has a point, goes through the point x naught, y naught, because, of course, how did we get y naught? We evaluated the function at x naught. Okay, so this point's the same for both the tangent line and the function, but now we're looking at how the function, the change in the function actually differs from the change predicted by the tangent line. And we call this, the difference between these predictions, the discrepancy. Okay, the discrepancy is what? Well, it's this difference here, which is f of x minus y predicted by the tangent. Okay? And y predicted by the tangent, of course, is y naught plus f prime of x naught times x minus x naught. And y naught is f of x naught. So we rewrite this as f of x minus f of x naught, which is what? There's f of x, there's y naught equals f of x naught. It's this change minus the change predicted by the tangent line, which is slope times run. You know, slope times run, this difference. And that's the difference between the actual predicted change. And we see in this case that by the time we get this far away from our original value of x, y has changed by significantly more than would be predicted by the tangent line. Now maybe the prediction of our tangent line would be sufficient, would be good enough, but we're off by probably about 30% between this change and this change. Okay, this change looks like only about 70% of this change. And well, I won't comment on that. Okay, so bottom line, prediction of our tangent line approximates the change in the value of the actual function. Okay, and that's really the change predicted by the tangent line approximates the change in the value of the actual function. Okay, now we'll go on to an example and see how this can be of benefit.